This is a mini lecture on multi-layer neural networks for data mining. My name is Ethan Parks. This is actually a final project for a course called Info 523 Data Mining, instructed by Dr. Cristian Roman Palacios. And this is specifically being taught at the University of Arizona College of Information Science. So first, I want to go into some of the neural network basics themselves. So what is a neural network? A neural network is an algorithm that basically loosely represents the human brain through a fashion of interconnected nodes in a layered structure. Neural networks tend to oftentimes be implemented for very complex analysis tasks themselves. So a lot of times this includes nonlinear data sources, which is one of the key strengths of neural networks, is they perform very well in nonlinear data. But because of these complex tasks, they often get labeled as black box algorithms, and this is specifically due to their problem of interpretability. The more complex these networks get, the harder it is for us to actually determine what's going on under the hood. Lastly, with this specific lecture, I'm going to be taking a supervised approach so that we can kind of build off of the supervised learning mining methods that we discussed in class. Specifically, we were kind of going into regression techniques. So I just want to show how this can also apply to that, and this can, again, be an extension of that for data mining. So before we go too deep into neural networks themselves, one thing we do have to cover is a topic of tensors. Tensors are foundational to machine learning, and more specifically, neural networks. Neural networks require the data to actually be represented as tensors themselves to be input into the network. And these tensors can basically be thought of as multi-dimensional arrays, or maybe more generally data storage containers. So these arrays are defined typically by the number of axes that they have, the shape of the tensors, and the actual data types included as well. So these data types are most commonly going to be numerical data, but again, we could see other categories such as Boolean values, text data, among various others as well. When we actually start talking about naming these tensors, they start often as being rank 0 tensors, which are considered scalar values, and then it progresses to the n number of dimensions that the tensor represents. So first order of operations here are going to be called tensor operations. And when we think about tensor operations, the main ideas I want to get across here are how the tensors flow through the network, and then what the actual purpose of the activation functions are. So when we think about the flow of the tensors, first we can see that we take the weighted sum of the previous inputs, whether that be the input layer or the outputs from a previous hidden layer of neurons. We add the bias onto that, and then that gets passed through what's called an activation function to produce the output of that neuron. Really, the main goal of the activation function here is to introduce nonlinearity to the model, which allows us to expand upon the actual hypothesis space for which the network's able to determine different patterns from. And when we think about the activation function as well, these functions have to be differentiable for backpropagation to occur, because backpropagation is, again, the actual workhorse behind how neural networks learn, and we'll see later how that happens in terms of the derivations that we have to make. The two specific activation functions that I want to highlight here are called the rectified linear unit and the sigmoid activation function. So the rectified linear unit is probably going to be the most common type of activation function we see. It's a more modern approach that was designed, and it basically aids with backpropagation and the vanishing gradient issue that people tend to see. But the one issue with this method is that they call it the dying ReLU issue. So basically when a neuron outputs a 0, that ends up killing that neuron for the rest of the process, and it's really hard for it to actually end up coming back. So we can see that a lot of the neurons within our network can end up dying off essentially because of that activation function. And then lastly, we have the sigmoid function, again, a very common activation function that basically maps the input values to an output range between 0 and 1. And this is, again, common for binary classification problems. So now that the data has passed through all the different layers of our neural network, we want to make sure that we're looking at the predicted value versus the true target value that our supervised model is being trained on. So to do this, we use something called a loss function, and the loss function computes what's called a loss score, and that basically allows us to determine how far off our model currently is. So going into just a brief overview of the loss computation itself, there's many different methods that are involved in neural networks for this. Two of the most common types that we're going to run into are mean squared error and binary cross entropy. So mean square error, I'm sure most people have actually come across at some point in time, where it's just the average of the squares of the differences between the predicted and true values. And this is very common for regression type problems that neural networks are trying to solve. Binary cross entropy, on the other hand, is a equation where the loss increases as the predicted probability strays from the actual true label. And so this is really common for models with output probabilities between 0 and 1, and so binary classification tends to be focused on this method. So now that we've actually made our first full pass through the model itself, we go to the backside where we actually do the learning portion of this. So this is done specifically through backpropagation and some form of an optimization method. Typically this is through gradient descent, but we'll see exactly how the model ends up shifting weights so that it can perform better on tasks. So specifically, let's say lay a little bit of foundation on what backpropagation is. First, we talked about our loss function that we defined earlier. That's computed on a single example in the data set, while the actual cost function is the average of the losses across all of the examples in the data set. So backpropagation itself actually just calculates the gradient of the cost function with respect to each weight in the network. And that's really important because computing the gradient of the cost function actually gives a direction and magnitude of the steepest ascent. And while this doesn't make sense right now, this is very important to the actual gradient descent method, which again, we'll touch in a little bit more detail on the next couple slides. So lastly though, gradient descent then uses these gradients so that it can update the weights in a way that minimizes the actual cost function itself. All right, now we're actually going to dive into a little bit more of a concrete example mathematically of how backpropagation works, because again, this is just a build intuition. So first here, I'll use my cursor to kind of point out the different sections of the flow chart here that are actually important, but we have just a fake example of a neural network here. We have our inputs denoted by X, our biases denoted by B, and then A for all our activation functions within our neurons. That includes the summation portion and the actual activation function itself. So mathematically looking at this, we can see that Z itself denotes the summation function. So again, we have our weights, our inputs, which in this case are the actual input layers, but in the other cases are just the outputs of previous neurons, and the actual biases themselves. And then within the neuron itself, we also have the activation function denoted by A, as we noted, and Z is again part of that, it passes through that activation function, which is in this case a sigmoid. And so again, this is the same throughout all the models, and we have our output neuron here, which then produces y hat, which is our predicted value, and we'll just pick some loss function here. So for example, we'll use mean squared error. That could be something different, and it probably would be better to use a different loss function if we were actually trying to consider the model itself. But just since mean square error is an actual common one to look at, we'll just stick with that for example's sake. So now if we think about backpropagation, really the thing we want to think about is how does the change in a weight affect the actual sensitivity of the loss function itself. And so for a simplest example, we could look at this weight right here, W31, which is again denoted by this red bar. All these red bars between the activation neurons, again, can be thought of as weights here. And we say, how does the shift in this weight affect the sensitivity of the loss function? And we can do that for each of these within this network itself. So if we say, how does this weight right here affect the actual loss function itself? We have to remember that that can be computed, but that's going to affect a lot more things throughout the network. So again, it's going to adjust various different summation and activation functions at different levels in the actual network itself. And so that's where we start to use this concept of the chain method in calculus to where we can then end up computing that. So for completeness in this exercise, I just want to walk through a quick example that just is very simple and kind of builds, again, some of that intuition. So if we look here at our weight, we have our weight W31. We want to say, how does a change in that weight affect the sensitivity of our loss function here? So mathematically, we're basically saying, what is the derivative of the loss function with respect to that weight? As we can see down here, what we do now is we say, all right, this weight is located first within the summation function. So because it's located within Z, we want to take the derivative of Z with respect to that weight itself. Next, what gets affected is Z is again passed through the activation function, our sigmoid, and that's denoted by A. So we say, okay, we want to take the derivative of A with respect to Z itself, because that's the next step in our actual chain of the network. And then lastly, this A value, again, can be thought of as y hat here because it's the prediction, the output node here. And so lastly, we want to say, what is the derivative of the loss function itself, or with respect to A, the activation neuron itself. And so that basically just gives us the backpropagated weight for just that specific example and that specific weight. What happens then is that specific calculation that we just made is an average across all examples in the data set. And then that is just one part of the actual gradient vector itself. And again, remember, the gradient vector itself is just the partial derivative of the cost function with respect to all the weights and biases within our network itself. So now that we kind of have a better understanding of how backpropagation works, we're going to take a brief look at the optimization methods of gradient descent, which is kind of your classic optimization within neural networks itself. Essentially what gradient descent does is that it takes those gradients that we computed through backpropagation and takes the negative of that gradient, which gives us essentially the steepest descent. So as we had explained earlier, the gradient computed by backpropagation itself is the steepest descent, so taking the negative of that just gives the steepest descent, which is important for us in minimizing the cost function itself. The equation for gradient descent is shown below. The Greek letter eta is used as the learning rate, and essentially what the learning rate does is it adjusts the sizing of the weight updates themselves, and it basically changes the speed at which gradient descent happens. So you can see in the chart up above to the right, the learning rate basically shows it stepping down on the curve. The big thing to note there is the actual sizing of the learning rate is important, because if we take too big of a size, what we can do is we can miss a minimum, whether it's local or global, and we could just end up somewhere random on the curve, which doesn't really help us in actual optimization. But if we take too small of a rate, we could get stuck in a local minimum, which is just not the most optimal solution there. So to just give a better example of that, I included the chart to the bottom right there, because it kind of shows the method of optimization, specifically gradient descent working in a 3D space. Again, in the higher dimension than this, it's impossible for us to really visualize clearly, but I just wanted to show that because it kind of, again, builds on some of the intuition of how these optimization methods work. Well, we made it through all the background information on the actual neural network algorithm itself. So now I want to shift topics into the actual worked example of a neural network in a data mining sense. So specifically, I just want to quickly run through the background of what data mining is. Again, data mining is just the process of data cleaning, sourcing or integrating data from multiple sources, selecting the right data to be using and the features that we need, transforming the data to be used for the mining task itself, data mining, again, which in this case will be using the neural network, and then performing the pattern evaluation so that we can present knowledge that's important for making decisions or actionable changes. So before I go into any of the code, I first wanted to start with the data sourcing and pre-processing I did with the neural network data. So first I wanted to identify the reliable sources with sufficient data so that we don't overfit our model. So in the case that I did, I decided to create a neural network data mining example on stock data. I wanted to specifically use the network to essentially create an indicator that would show whether or not there's going to be movement in the stock using some lagged variables. So first I wanted to make sure that I'm using a source that actually has robust data sets for this. And so in Python, there's a library called yfinance, which is just Yahoo Finance stock data. And they have thousands and millions of records of all sorts of different indices. So I decided to choose one on the hourly basis so we can have sufficient sample sizes. Next, I wanted to do some feature engineering on that so that we can have some derived variables that are better representative and could hopefully help us categorize the target correctly. And I also wanted to address any sort of missing data or mixed data types or any sort of non-production form data that we might have to modify so that we can actually use the information we get from this later. I also wanted to perform some scaling and normalization of the data. Specifically, this is really important for neural networks because you don't want to introduce any sort of bias due to the actual values of the data itself. So I just use a standard scaler, which just takes the value minus the mean over the standard deviation. And then again, this just produces homogeneous ranges of all the features, creates a mean of 0 and a standard deviation of 1. And then lastly, wanted to split the data into different training and test sets. This is again very important so that we can actually evaluate how well our model is doing so that we can hopefully have information that can be useful to other people. And so this is just 4 different sets of features and targets, typically with 80% going to training and 20% going to testing. So in the actual code itself, I'll just briefly show this so people can see how I had both sourced the data and then also pre-processed it. So like I mentioned before, I got most of this from yfinance. It's just really easy, clean data sets, and they have pretty robust amounts of data depending on what you're looking for. So basically just choose the ticker symbol that you want, select the start and end date for the interval, and then select the actual interval itself. So I chose hourly data just because of the amount that I was able to get. But after getting that data, basically I did a lot of feature engineering on this data set itself. So creating new features, modifying old ones, encoding others, just so I can get a data set that's better representative for hopefully our classification tasks that we want to do with the neural networks. And this just gives an example of how the data was called later. So again, we have our ticker symbols, our start and end dates, creating our objects to perform the actual data set modifications themselves, and then subsetting our data down to the only features that we want. And then lastly, doing some additional pre-processing that we can see here. So time pre-processing, splitting of the actual data set into train and test sets, and then using sklearn's standard scaler to scale the data itself. So now that we've actually gone through all of the data sourcing and pre-processing steps, the data mining step is now the task at hand. So the key concept here is to really understand what is the knowledge we're trying to represent with the actual data mining process here, and what's the best route of doing that. So for example, neural networks are great, but they're oftentimes very complex, and there could be a more simple algorithm that could be applied that's more efficient but achieves almost the same level of accuracy, which gives us the knowledge we're looking for. If we do want to use neural networks, understanding what the different architectures are and when to apply those. So, when do you use a multi-layer perceptron feed-forward network versus a convolutional neural network? And if you do choose to use one of those, then understanding the proper mechanics behind them so that we can achieve the desired results. So, when to use certain type of activation functions, when to use certain loss functions, because all of those are going to affect the accuracy, which again affects the quality of the data that we actually are mining here. So in the actual data mining example itself, I ended up producing a simple feed-forward neural network here. I used a library called Keras, which is essentially a deep learning library built off of TensorFlow. And again, it just uses CPUs, GPUs, and TPUs for the actual computations themselves. So specifically, I ended up using just a standard sequential model here, and then added 4 different layers. First layer being the inputs of 10 neurons, and then 2 hidden layers themselves, one of 8 neurons and another of 5 neurons. All 3 of those use the Rayleigh activation function, and finally the output layer with a single unit using the sigmoid activation function. During the compiling phase, I ended up adding a loss of binary cross entropy, which again we covered earlier. And for the optimizer, I chose an ATOM optimizer. Initially, I started with a stochastic gradient descent, but found that this actually performed much better. And again, it represents some of those examples for additional optimization methods that we can have. Lastly, this was again fit on the training data, and as you can see in the initialization function, the epochs were set to 15 epochs, which means the model cycled through the training data set 15 different times, and a batch size was set to 32, which means that the weights aren't adjusted until 32 examples have gone through themselves. After the data mining process itself, we want to start going into the evaluation phase, where we're really trying to test how accurate is the information that we are mining from the data. And this, again, with neural networks, is going to come down to hyperparameter tuning, just so that we can ensure that we have the most robust model that we can for the classification purposes. We also want to make sure that there are multiple accuracy measures being used, along with any other additional considerations, such as, is this model the correct model for the problem? Is there an issue with the base data set itself that's not robust enough to predict those targets? So in the model that I created, I achieved an 80% train and test accuracy, which sounds great off the bat, but again, can we just rely on that one metric? I can tell you that the answer is no to that. Here I have the actual density plot of the predictions for values of 0 and 1, and we can see if it's below 50% or 0.5, it should be classified as 0, and above that should be classified as a 1. But we can see here this is an example of a class imbalance issue, because there tend to be more zeros in the target data set than there are ones, and so this produces many false negatives here, and so the true positive accuracy goes down to approximately 40%. And this is just one of the examples for why we have to go back and evaluate our models so that we can make sure that we're mining the correct data. Additionally, I wanted to show the actual, the classifications, the true classifications themselves, and then the predicted ones. And so this can kind of show where a model might be struggling. So again, the predicted values are on the top with the actual true labels on the bottom. And while the predicted labels do have a few instances where it does look like it's performing correctly, so for example, we have a pattern here, and then we're supposed to see a big drop off. That's essentially what our model's trying to do, is find or predict some points within a chopping pattern and then show movement right after that. We go down and we look at the actual true label data set, and we can see that not only is it a class and balance issue, but this is probably a data set issue in general, because this is too much noise in our data, and it's really not pointing out many relevant features here in the data. We can see a few examples of good indicators and then a move, good indicators and a move, but that's not always the case. And so we really want to go back and again start to reevaluate our data set and start to make those improvements so that we can present the most accurate knowledge possible. Finally, after all of the data mining steps comes the knowledge presentation phase. And this is just simply where the data is transferred to a setting that it can be rendered relevant for any sort of actionable purpose. In the case of the financial stock data mining that I had performed with the neural network, this could be something such as taking the model and integrating it to an investment platform to aid in real-time decision making. It could be any sort of dashboards to business leaders to monitor stock movement. It could also be just recurring reports to financial advisors to help them manage client portfolios. So any sort of suite of products that could help people make decisions based on the data that we did mine here. So just a few concluding thoughts on the matter. Really the main goal I wanted to focus on here is that we need to ensure that knowledge representation is the key of what we're trying to do in data mining. And so this is the guiding principle for which all the other steps fall in line too. With neural networks, we always want to start simple and then build up where only necessary. We don't want to start with the most advanced deep learning network, because the simplest network could also work just as well in that situation. We also want to make sure that when we're trying to understand neural networks, we're understanding the theoretical foundation of them, but we're also gaining intuition from the applied cases as well. And those typically will yield the best results. But even above any sort of modeling perspective, time invested into the baseline data development will always yield the best results for the underlying knowledge that we're trying to extract. So with that, that is the final presentation for the lecture here. Just a few final books that I just wanted to call out. Data Mining Concepts and Techniques by Jaiwei Han is a great book for just understanding just a suite of data mining concepts related to all sorts of different algorithms. It's kind of where I got the idea for using neural networks here. To actually understand the neural networks themselves, there are plenty of books online, but really I think a great starting point is the Deep Learning with Python book by Francois Chollet. The second edition is a little bit more updated to what the current libraries are situated as, but I would totally recommend that. And then lastly, I will make sure to include my GitHub repo in the description of this video. So again, thank you for watching, and if you have any questions or comments, please leave them down below. Thank you.